Bismillahirrahmanirrahim. Assalamu alaikum. Welcome to the Electrical Engineering channel. In this lecture, I will discuss how the power of a matrix can be evaluated in the simplest way using eigenvalues and eigenvectors. So, if we are evaluating the square of a matrix A, it means we have to multiply that matrix with itself two times. If we are taking the fifth power of a matrix or A raised to power 5, then that matrix has to be multiplied with itself five times. So this multiplication of matrices is complicated, right? And the cost of multiplication of a matrix is high. But we can do this multiplication in the simplest way using eigenvalues and eigenvectors method, and that method will be discussed in today's lecture. So if we are evaluating the square of a matrix, then we should know that the eigenvalues of A square are lambda square, lambda 1 square, lambda 2 square, and so on up to lambda n square. So it means if the matrix is multiplied with itself, then all eigenvalues will be squared as well. If we are evaluating the eigenvalues of A raised to power 5, then the eigenvalues will also be lambda 1 raised to power 5, lambda 2 raised to power 5, and so on up to lambda n raised to power 5. And A matrix is an n by n matrix. But every eigenvector of A is also an eigenvector of A square. So the eigenvectors of any power of the original matrix will not change. If the eigenvectors of A are x1, x2, x3, then the eigenvectors of A square will also be x1, x2, x3, and so on. So we can prove this property. This is a very simple proof because we know that Ax is equal to lambda x. Now let's multiply this equation with A from the left hand side. So it will become A square x, and that will be equal to A lambda x. Now lambda is a scalar, so we can take it out at the left hand side. So it will become lambda times Ax. Now again, Ax is equal to lambda x. So A square x will be equal to lambda times lambda x. So that will be equal to lambda square x. So it means A square x is equal to lambda square x. So clearly from this equation, we can conclude two important points. First important point is that since Ax equal to lambda x, and in that equation, x was the eigenvector of A and lambda was the eigenvalue of A. Now we have A square x equal to lambda square x. So the first point is that the eigenvalues of A square are lambda square. So eigenvalues will be squared, and x was the eigenvector of A. Here again, x is the eigenvector of A square as well. So these are the two important points which can be concluded from this second equation. Even if we have A raised to power 5x, that will be equal to lambda raised to power 5x. So the eigenvalues will be lambda raised to power 5, but the eigenvector still will be equal to x. So that won't be, there won't be any difference in the eigenvector. So that is a very simple and informative proof. So thus lambda square is eigenvalue of A square with the same eigenvector x. Alternatively, we know that lambda equal to S inverse AS, right? We know that from previous lecture, we know that capital lambda is equal to S inverse AS. So capital lambda square will be equal to S inverse AX multiplied by S inverse AS. So when we multiply these two equations, we will see that this S will be cancelled out with this S inverse, and we will have S inverse A square S, right? S inverse A square S, and that will be equal to lambda square. So again, we know that if we have the square of this original matrix A, the eigenvalues will also be squared, but the eigenvectors are the same. So eigenvector matrix is still equal to S. There is no S square or any power of S which has been changed. So lambda square are the eigenvalues of A square, and lambda raised to power k are the eigenvalues of A raised to power k. Even if this k is equal to -1, then in that case Ax will be equal to lambda x. So uh, 1 by lambda will be equal to A inverse X. So the eigenvalues of A inverse are equal to 1 over lambda. So lambda values will also be inversed, or reciprocal of the lambda will be the eigenvalue of the A inverse matrix. So the eigenvalues of A inverse are 1 over lambda. So now how to compute A raised to power k? From earlier discussion, we know that S inverse A square S is equal to lambda square, and also S inverse A raised to power k S is equal to lambda raised to power k. And we can also write A raised to power k is equal to S lambda raised to power k S inverse. So remember, lambda is a diagonal matrix with eigenvalues at the diagonal, right? So this is the lambda matrix, which is equal to lambda 1 0 0 lambda. So any power of this diagonal matrix can be evaluated by taking the same power of the diagonal entries. So lambda raised to power k is equal to lambda 1 0 0 lambda 2 raised to power k, and that power k will be equal to lambda 1 raised to power k 0 0 lambda 2 raised to power k. So whenever we have a diagonal matrix, any power of that matrix can be evaluated by taking the individual power of the diagonal entry. So that will be equal to lambda 1 raised to power k and lambda 2 raised to power k. All other off diagonal entries will remain equal to 0. So this thing is very simple. And if we are evaluating any power of A, then we just have to evaluate the matrix of eigenvectors of A, which is S. Then we have to take the inverse of this matrix S, which is S inverse. And then we have to take the same power of the lambda matrix. So that uh, same power of that lambda matrix is very simple, because we have to just evaluate the individual powers of the eigenvalues. So that will be lambda raised to power k matrix, and then these three matrices will be multiplied with each other, and then we will get A raised to power k. In other case, if we are evaluating A raised to power 10 or A raised to power 5, then we have to write this A matrix 5 or 10 times, and then we have to multiply those five matrices. So that would have taken much longer, but this process is very simple, and this is less time consuming. Okay, so how to compute A inverse? So we know that A is equal to S lambda S inverse. So it means S in A inverse will be equal to S lambda S inverse whole inverse. And we know that ABC whole inverse is equal to C inverse B inverse A inverse. And this A inverse will be equal to S inverse whole inverse lambda inverse into S inverse. So this will become S lambda inverse S inverse, and lambda is equal to lambda 1 0 0 lambda 2, and this lambda inverse again will be equal to 1 over lambda 1 and 1 over lambda 2, because this is a diagonal matrix. So if we are taking lambda raised to power minus 1, it will correspond to this lambda 1 raised to power minus 1 and this individual lambda 2 raised to power minus 1. So lambda raised to power minus 1 will be equal to 1 over lambda 1 and 1 over lambda 2, because this is a diagonal matrix, and any power of this diagonal matrix can be evaluated by taking the individual powers of the diagonal entries. So let's solve an example, and in this case, after evaluating this lambda inverse, we can evaluate this product of three matrices, and that will give us the inverse of this matrix A, right? So this is A inverse. So I by mistake missed power minus 1 of this A matrix. So um, this is A inverse, which is equal to S lambda inverse S inverse. So let's solve this example, and in this example, we will evaluate the inverse of this matrix A, and the two eigenvalues of this matrix are minus 1 0 0 5. This is the S matrix, matrix of eigenvectors, minus 2 1 1 1. And the inverse of this S matrix, S inverse, is equal to minus 1 by 3 1 by 3 1 by 3 and 1 by 3. So A inverse will be equal to S lambda inverse S inverse. We have all these three matrices. Let's multiply them together, and at the end we will get minus 3 by 5, 4 by 5, 2 by 5, and minus 1 by 5. So I have written a simple code to demonstrate you if this method of eigenvalues and eigenvectors actually works or not. So we can check it. We have this system matrix A which is equal to 1, 4, 2, 3. So let's evaluate the matrices of eigenvectors and eigenvalues. This is our S matrix, this is our lambda matrix, and this command will give us S matrix and lambda matrix. So let's evaluate A raised to power 5. Let's evaluate A raised to power 5 by using this eigenvalue method. So A raised to power 5 will be equal to S lambda raised to power 5 multiplied by S inverse. So this will give us A raised to power 5 by using this eigenvalue method, and we will evaluate A raised to power 5 in the conventional method as well. So we can compare our answer. Similarly, we can evaluate inverse of this matrix A by using eigenvalue method, and that will be equal to S lambda inverse into S inverse, right? Which is also given in this example, S lambda inverse S inverse. So S lambda inverse S inverse, and then we will compare our answer with the actual inverse of this A matrix. So let's run this code, and after running this code, we have the result over here. This is A raised to power 5 using the eigenvalue method. This is A raised to power 5 using the conventional method, and we can see both results are same. Similarly, this is the inverse of A using eigenvalue method, and this is the inverse of A using the conventional method. And this is the same answer that we have obtained in this lecture. You can see minus 3 by 5 is the first entry, so that is equal to minus 0.6. This is 0.8, this is 0.4, and this is minus 0.8. So that is all about our today's lecture, and I hope you have clearly understood how to evaluate power of a matrix and inverse of a matrix using eigenvalue method. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.